Okay, ahoy! Ja się Mike. A że potoshime Wyrodny Karol Čapek. We know this? How did I do? Is it very bad? Was that awful? Sorry, I had to try. So I have a few things first. Since I travel quite a bit, I need evidence, so I need to take your picture. So first, everyone say hello, ahoy. Excellent, okay, so now we're done with that. Okay, so the name of my talk is this Dreams, Lies, and Autonomous Web. But first I want to say, we are under the rule of the robots, eh? So I first learned of Karol Čapek through a book that translates in English to The Absolute at Large. 1922, it's a novel about someone who invents a machine that does all the work of humans. And humans have no more jobs. There's an odd side effect to the machine. People near it, when it's working, get very religious, but that's just a side effect. But he has predicted almost 100 years ago that robots will take all the jobs. Of course, a book that most people associate with Karol Čapek is this Rossum's Universal Robots. Karol and his brother Josef invent the word robota, use the word robota in a way that no one had used it before. And in this play, robots destroy humanity and take over the world. 100 years ago, here is an author who has explained already the end of all jobs and the final robot apocalypse. Right here. So I'm so happy to be here. But of course, wait, I've already talked about the end of everything and I've only just begun. So maybe I need to back up just a little bit. Okay, so first, this is me. This is how you find me on LinkedIn and Twitter and GitHub, and I would love to connect with you and learn about what you're working on and what you're doing in the world of software. I work for a group called API Academy, which allows me to travel all around the world, as Daniel already mentioned. I'm very lucky I get to meet some of the smartest people in the world and learn what they're working on. And this talk is about some of the things that I've learned in the last few years. And it makes me think about what is the future of the web and what is the future of machines in general. So we're in an amazing age. We're at a crossroads where we have more and more devices. You know, Avi in the talk before us talked about all these devices people are trying to create to connect to things. And there's lots of challenge to this. So there's predictions that we will have 50 billion devices sometime soon. We have lots and lots of programming languages. We keep inventing new programming languages because we're struggling to try to get a hold of how we control and manipulate things. We're getting more and more pieces of software downloaded all the time. Almost every time I pick up my phone, it's asking me to download and update for something else. So we have all this software, all this material, and we have all these things called APIs, application programming interfaces, connections from machine to machine, usually over the web or over the internet, which is an extreme challenge, a huge challenge to do. And they keep growing larger and larger. So as we get more devices, and we get more devices on machines, in buildings, on cars, all these other things, there's a huge challenge ahead of us to figure out how to manage this. Because it turns out none of this behaves the way we would expect, often the way we wish. We want assistance everywhere we go. We want a smart house like Avi talked about. We want cars that drive themselves. The problem with every one of these examples is they interact with real life. And real life is not programmable in the way we think machines are programmable. In fact, we're headed for this huge mess. We even experience a lot of it today. Many of us who work in a web space or work with APIs on the web, we know that lots of things don't work the way we expect. There's lots of bugs, and connecting them is incredibly costly and expensive. So along with this idea of automation, we have this other big idea of big data. There's lots of data out there, and that maybe big data somehow is going to solve some problems for us. So we're using lots of neural networks. We're trying to see if we can't teach machines using big data. If we can give them enough data, maybe they can learn something that we can't tell them. Often we're thinking of trying to mimic the way the brain works. A gentleman by the name of Mel Conway, you might have heard of him from Conway's Law. Mel Conway once said that the job of a brain is to make a brain. It's to learn. It's not to learn a specific thing, but to learn in general. And one of the challenges when we write software is we hardly ever write that software. We write the software to do one thing. We don't write the software to learn to do something. That's a very different kind of software. More importantly, most of us write software for this. We write software for one machine. We test it on one machine. We put all the data on one machine. And then we let it loose. And the problem is, it isn't one machine. It's a network of machines. And in fact, most of the things that we are taught in school, most of the things we read about, most of the programming tools we have today are all about helping us program just one machine. And that's not enough. Because we're living in a world where there are lots and lots of machines, billions, as we've already talked about. And those billions of machines need to be able to interact with each other. And they need to be able to do it in what we call at the Academy a safe, cheap, and easy way. They need to be able to connect safely to machines they have never met before. We need to build a very different kind of network. The kind of network that looks like just a web, a series of bits and bytes connected to each other. And more specifically, a kind of network that changes every single day. In our brains, neurons reprogram themselves every single day. That's how we learn. So we have to build that as well. We have to learn to program the network itself. And that's a huge challenge for most of us because that's not really the way we're taught. So as we go through this next several decades, I'm reminded of this great comment. Those who cannot remember the past are condemned to repeat it. And this can apply in lots and lots of ways. Avi talked about this in the previous session, where if we don't pay attention, we realize this has already been invented a long time ago and we forgot, so we reinvent it again. And while I love this phrase, there's another phrase I like even more. Those who ignore the mistakes of the future are bound to make them. Think about what that means. We have a future ahead of us, and it's easy to take the easy path, to make some mistakes, to do things in ways that aren't necessarily in everyone's best interest in the long term, but are in the short term. I think we're experiencing this in the United States. England has experienced this as well. Facebook is struggling very much today with this notion of how they optimized for lots of profits today, but did not think quite about what would happen in the future. So as we program machines, we have other responsibilities as well, and that responsibility is to the future. So I want to spend the remaining time, we've got about 30 minutes, I want to spend the remaining time talking about what that future could be like and what responsibilities and roles we have in it. And to do that, I want to quote André Gide, "One does not discover new lands without consenting to lose sight of the shore for a very long time." Think of Columbus, think of Magellan, think of everyone from Europe who decided to sail the Atlantic the first time without ever seeing a coastline. And they would go for months without seeing land. That took a lot of guts, that took a lot of nerve, a lot of courage. Didn't always work out so well, but we remember the ones that did. That's what we're going to do today. We're going to lose sight of the shore for just a little while and talk about a few things. So I want to talk about this notion of dreams. We all experience them. In fact, dreams are this sort of weird hallucination, this weird combination. In our brains, we use dreams to practice as well as to project into the future. This image, by the way, is actually from a Google program called Google Dreams. And it's actually, these deep dreams programs create images from information that's already collected. These are all images that were created by Google Deep Dream. Trying to get machines to hallucinate, trying to get machines to think about things, imagine things, is a really important aspect to programming the future. If we want machines to be autonomous, they need to have some of the same abilities to project into the future, to imagine, to create archetypes that they can practice, that they can recognize in the real world. And it helps us learn about the brain. It helps us learn about how our brain works as well. Our brain is an amazing thing, by the way. Brains are the way we hallucinate, we imagine. By the way, that hallucination, that imagination allows us the capacity to lie, right? We can lie about the past. We can project into the future. We can convince others of other things. We get to practice in our brains. There's lots of research that says if you're an athlete or a musician or an artist or you have some manipulative skill, you can practice in your head. I practice my talks in my head. It's the way we learn. Now, big data comes into this a lot when we talk about machinery. This is a building built in the United States. It's called Bumble Hive, and it's thought to be able to store 1 yottabyte of storage, or 1 million terabytes of data. In the United States, we're collecting all this data from Facebook and apps and phones and everything else, and we're storing it in this big room. Well, how does storage work in the brain? Turns out the brain, it's a little debatable. The brain holds about 100 terabytes of data. It could hold 100 terabytes of data, which is about 100,000 gig. And it turns out in our daily activities, we usually collect up about 2 to 4 gigs of data every single day. So our brain has the power to save 250 years of information, each person. That's pretty amazing, right? Especially since, we're lucky if we make it to 80 or 90. But the thing is, what is the brain doing with all that storage space? What is the brain doing? Does it actually store every bit of experience, every bit of data, every occurrence, every visit that we make? I know it doesn't because I meet people every day and I can't remember their names. So is it stored somewhere? It turns out no. Our brains do not store every experience we ever have. In fact, there's a very mature and complex process of distilling our daily experiences into something that we would call a memory. Memories are actually manufactured bits. Memories are not things that are just imprinted on us. Memories are things that we create. We create the stories that we remember. And this ability to create a memory is really important. We prune data and place it in long-term memory. We summarize and store. We summarize, label, and store. And in fact, we do this mostly during sleep. Sleep deprivation, one of the biggest problems with sleep deprivation is that we cannot create memories. This is this great book called The Secret World of Sleep, which talks a lot about this. And in that book, it actually identifies a person, a type of person who cannot erase memories. They actually remember everything. And it is debilitating. Every sound, every smell, every touch, every look calls up another memory, and they can't control it. And it drives them mad. They can't easily exist in the world because the memories, the past, keeps intruding upon the present, and they cannot live in the present. So forgetting is incredibly important. Forgetting is how we get by. Forgetting is how we get past terrible experiences. Forgetting is how I not clutter my brain with lots of material that the signs I saw, the cars I saw, the tram, the subway, all these. I can't afford to keep all of that. So forgetting is incredibly important because forgetting helps us cope with the world, and forgetting lets us write our story through the use of memory. But choosing is also important. So this is a real difficulty in computing. We can get computers to pay attention to a lot of data, but how do we tell them which piece of data to select? Which piece to remember? Which to choose when they have a series of options? Learning to choose is very hard. Even we know as children, if you have small children, teaching them to be able to choose what to wear the very next day or what they want to eat. They change their minds constantly because they haven't learned this process of choosing. Learning to choose is hard. Learning to choose well is even harder. And Barry Schwartz, in his book, he talks about learning to choose well in a world of unlimited possibilities is almost too hard. We have this idea, the notion that you have all these possible choices actually make it worse, so that when you finally make a choice, you regret your choice because there were so many other possibilities that you don't know about. So Barry talks about this in the book, The Paradox of Choice. It turns out having too many choices makes us unhappy. And we're constantly surrounded by too many choices everywhere. Everywhere is too many choices. So there's a real challenge. So it turns out this whole process of sleep and waking is incredibly important for constructing the memories and for practicing and for learning. Here's a little trick. Here's a little sleep trick I'll tell you that I learned. If you want to remember what happened during the day better, go to sleep early, because that early sleep is where you consolidate your memories from the day. If you want to think creatively about a problem and help come up with creative solutions, sleep in late, because it's that last bit of deep sleep where you practice and you hallucinate and you work on problems that you already have. So now I tell my wife, there's lots I have to remember and I have a lot of creative work to do, so I will be sleeping in, I'll be going to bed early and sleeping in every night. I never get up. But this idea of learning to sort of hack the brain is incredibly important. There's another big problem with big data. Edward Tufte, who creates lots of great visualizations of data, has this great line: if you torture big data long enough, it will tell you exactly what you want to know. Right? We have to be very careful in this choosing process that we don't just keep choosing the things that confirm what we already suspect. And of course, that's exactly the Facebook problem, right? Those of us in social media, we end up choosing the things that confirm what we already suspect, even if those things are not true. And we create memories, and we create stories, and that's how we operate our brains, and that's how we go out into the world with this information. Now, if we want to build a web of autonomous machines that can talk to each other, we're going to have to teach them to hallucinate. We're going to have to teach them how to figure out how to practice, how to imagine, how to project, how to talk about a goal and get there. We're also going to have to teach machines how to forget. We're going to have to give up this notion that all we want is every bit of data we ever have. And what we want instead is machines that can create their own memories, their own stories, in order to get somewhere. Now, I want to talk about another thing very important before we get on to the next step, and that is what I call lies. So this is a picture of one of the early Google test cars for automated driving. Lots of sensors, lots of devices, and all these other things on it. And you sort of get the sense that this pays attention to the landscape quite a bit. Turns out that's not really so true. I love Michael Lewis's quote. Michael Lewis wrote several very popular books, Moneyball, books about the crash of the stock market and so on and so forth. And he says a key is simple, a car is complicated, but driving the car in traffic, that's complex. The problem isn't the car, it's the traffic, right? And we've learned to drive in a space where we don't know, we can't predict what's going to happen next. Right? That's what we do. That's how humans drive. We don't know the whole traffic before we go out the door. If we had to know the whole traffic before we go out the door, we would never leave. But instead, we deal with what comes. It turns out that most automated driving technology, even still today, this is research that I was doing about 4 years ago, automated car technology simply memorizes the path and travels that path, and the sensors look out for unexpected things, and if it runs into unexpected things, the car simply stops. As a matter of fact, I don't have a slide for this, but I just learned a few months ago that Nissan Corporation is going to offer a service to automated car companies where there's a human that actually pays attention to any car that comes in that's driving, and if the car has a problem, it can call Nissan and say, there's a roadblock here, what do I do next? And the human reprograms the car around the obstacle. Right? So it's like software support for cars. Cars call, I can't get through here, and then they tell them how to get to the next step. Because cars don't deal with the unexpected. They simply turn off. All they know is the road that they have. If you look at what happens when you're watching one of these Google cars, all it does is follow a predetermined path. Finds an obstacle, it just simply stops and waits for a human to solve the problem. Cars are not yet designed to be autonomous. They're designed to simply operate safely in an environment that they already know. And that's one of the reasons that all these cars don't always operate everywhere. It's also one of the reasons that Tesla Automotive ends up reporting more accidents than others. Not that they report more accidents than humans, because they are trying to burst that envelope. It turns out in real life, We have this very unpredictable sense of things. This is a flock of birds that sort of follow each other. They don't follow each other because they know where they're going. They follow each other because they follow each other, right? A brain is made to build a brain. And it turns out most activities in life are very random. So this is a series of ants. It's a great series of books on ants and ant culture. There is no queen that tells everybody what to do in an ant colony. Ants decide themselves based on simple messages. There is nobody in charge in an ant colony. It's a lot like that flock of birds. There's nobody in charge. But the ants have actually survived for billions of years on the earth. And in fact, almost all life in bacteria and supercellular structures, there is no one in charge. They simply interact with each other in very small ways. This gives us a great opportunity to think about how we're going to manage machines. Because this world of complexity is not just statistics. It isn't just, pick the easiest way to make it from this location to the next. It's actually about interacting with things around you. IBM Watson is this really impressive technology that's pressed statistics to just about its edge. And it's actually going to do great things for us. But all it's really doing is predicting based on the past. It's not interacting. It turns out you can't get rid of the complexity if you want to actually advance the technology. We're coming up to a point, Google has already discovered this, we're coming up to a point where all their technology that's based on statistics, while they're still improving, they're getting to the point where there's less benefit than the past. We're coming to the end of the sort of simple version of the story. The simple version was use math. Big numbers are your friend, right? Well, now they're no longer paying off. We have to get to the next level, the next set of steps. Because learning is a complex system. Learning is different. Statistics is not learning. Statistics is just replay. I want to add one more thing that's come up in the last year or so, and that is this notion of bias. As we're introducing more machine learning, more AI style, more statistical feedback, as we're trying to get to this next level, we're discovering a great deal of bias. It turns out that machines bring more than just computing, they actually bring bias and assumption. And whose bias and assumption ends up in the machine? The programmers. The programmers' bias and assumptions. So several years ago, I think this was around 2009, HP released a camera that was supposed to track faces and found that it did not track faces of black people. This is an example of a camera that would help you if somebody had actually mistakenly blinked when you photographed someone. It turns out, however, this woman is Asian, and she kept getting the question, did someone blink? There have been several examples recently of this. Soap dispensers that will dispense to a white person's hand, but not a black person's hand. Here's an interesting one. When you would search on LinkedIn, for Stephanie Williams, the AI would say, I'm sorry, did you mean Stephen? And here's one that really surprised me. Voice recognition systems make more errors when they're listening to women's voices than men's voices. Now, the first few examples, in not being able to track a face on screen, having a problem with facial recognition because of the eyes, or having a problem with dispensing liquid, that is actually an implementation detail. Right? It turns out that we're using algorithms. Mostly in the case of skin, we're using algorithms for reflectivity, right? Darker skin doesn't reflect as much, so some of these systems don't work right, these photoelectric systems. That's something that's actually built into the software itself. And when that software is built and tested, it's being built and tested by people who don't encounter this problem. What does that mean? We've got a diversity problem in the team that's building the software. It's not designed in. It's not like somebody said, let's make sure that we treat Asian people a certain way with the software. Nobody does that. It turns out it's an unexpected consequence of the software we're building. And we're only now starting to see this unintended consequence. These last two, this one about LinkedIn and this one here about voice recognition, that's a different problem. That's actually the training data that we're giving a machine. The way voice recognition systems work is you train them. And it turns out, in this case, that this software is mostly trained by men. Again, it's a diversity problem. So in one case, it's coded in another case, it's learned. And that's really, really important, because it turns out the diversity of the group creating the product or service, when that doesn't reflect the diversity of the group using the product or service, suddenly we notice the bias. Notice what I said, we notice the bias. It's not like the bias wasn't always there. It always was. This has always been true. There's another word that we have for these assumptions and discovered biases. We've used the word for quite a long time. We call them bugs. Oh, I'm sorry, that interacted in a way I hadn't thought of. Now, bugs in particular, single piece of code are relatively easy to find, although you'll never find all of them. But as you start to connect machines together, you're going to find more and more instances of unexpected bias, unexpected assumptions, resulting in what we would call bugs. And that's why I love this sign that's here in the hall. Because this is really true in many, many cases. It's not actually a bug, it's just a random feature I didn't know it had. And in fact, brains have lots of random features. We make weird connections to things that can turn out to be very valuable, because the brain is all about making a brain. Okay, so let's talk about what we're really here to talk about. This autonomous web, this idea of how we can start to create machines that really do connect to each other. So I'm going to jump a little bit into information theory and complex systems, and then I'm going to talk about this word hypermedia, this way that we connect the web today. I'm going to go back to the 1880s, because I find this really interesting. James Clerk Maxwell was trying to see if he could beat the second law of thermodynamics and try to predict where atoms would be. And he knew that fast atoms were generating a lot of heat and slow atoms were not. He imagined, he had a thought experiment, if I had this little demon that could actually know which atoms are fast and slow and separate them, I could find out some interesting information. I could actually predict where things would be. Of course, it's just a thought experiment. About another decade later, Ludwig Boltzmann came up with this idea of entropy, Boltzmann entropy. It turns out that every possibility of where atoms might be in a single space exists all at one time, what we call the eigenstates, or the proper or characteristical state. And actually knowing where an atom is just a prediction of the number of possible possibilities. So all we can really do is predict the possible location of any particular thing. It takes years, it's several decades later. Claude Shannon, who was kind of considered the father of information theory, he gave us the parity bit. Claude Shannon was the one who thought up the notion that if I send a message and I need to check and see if it's actually the same message that is received, and I can do that by using a parity bit without ever understanding the contents of the message. Claude Shannon says the number of bits needed to represent something is actually his version of entropy, or what later gets known as surprisal. The surprise of the information is the things that were unexpected in its reply. This ability, this unexpected nature about information actually comes up in Turing, and Turing's what's called Turing's halting problem. Turing writes, if he wants to write an application, he comes up with this problem in 1930. Does he know when the application will end? Does he know when the computer program will end? It turns out he cannot accurately predict when any computer program will end. Again, we only have this vague notion of what's really going on. Finally, I love this trick Kurt Gödel, mathematician Kurt Gödel, gives us, and he basically comes up with this statement, this phrase, "This statement is unprovable." Is that true? Or is it false? What Kurt Gödel has done here is actually give us a little mental flip in the middle of a sentence. He's actually combined both the data and the program, the rules for deciding true and false, along with the data itself. And our minds kind of like get confused at this. If you watch lots of 1960s and 70s sci-fi films, usually a human would use some trick like this to blow up the evil machine that was going to take over the world. Right? They would use some trick of logic. Von Neumann, who came up with the way we think of computers today, also struck on this notion of storing data and program in the same physical space. In the beginning, they were two different things. We thought that we would have data in one place and program in another place, but he says, no, you mix them and match them. This allows us to create programs that write programs. So he comes up with this idea as well. So data and program are together. And it turns out that's exactly how life works. RNA messaging is data and program together. All single cell, even below single cell, and DNA and RNA all work on the notion of messages passed back and forth that can act as both program and as data. Now I want to mention one other person, Roy Fielding. Roy Fielding writes a dissertation in 2000 about this notion about how the web works, and he says the web is this place where you can only approximately know what the shape of it is. Machines can enter and leave, and the only way we can safely communicate is by messages back and forth, and the messages contain not just the data, but they also contain the instructions for the very next steps. We call them links and forms in the human web. That is the program, and then the rest of the display is the data. And it turns out large networks of components with no central control and simple operation, that's a complex system. That goes back to the ants that we talked about earlier. We can actually build these kinds of things. The other big thing about a complex system is it has its own behavior that emerges as a result. Behavior that is not owned by any one single component, but is the combination of many components. And the web itself is this kind of complex system. We have the perfect experimental grounds for building these kinds of things in the web itself. So I want to dig deep into what we have today on the web and what we can do. So if you program in the web today, you program in a thing called media types, messages that we pass back and forth, and they're registered with the IANA group. In the last few years, there have been several new media types created that are designed for this thing about program and data together. We use them in APIs in order to communicate back and forth. The more programming you can put in the message, the less code you have to write. And that makes it possible for a machine to learn over time without having to be reprogrammed. And it turns out these messages operate in this notion of surprisal, just like Claude Shannon had talked about, or Claude Shannon's version of entropy. There's a great story about how Claude came up with the name of entropy. It actually works opposite of what we think of the word entropy is about everything becoming random, but it's for another story. It turns out each media type has its own level of entropy or surprisal. There's this thing called the URI list, which just lists URIs. There's very little surprise here. Very little new information. We know exactly what's going to happen. However, plain text has lots of surprisal. We never know what's going to be in plain text. So we would have to do a lot to figure out what this plain text message is. HTML is kind of a good in-betweener. It actually marks out where the commands are, the A tag, the form, the IMG tag, the iframe, and where the data is. So it actually has a sort of a medium size of surprisal, but it doesn't decide exactly what order things come in. From a machine point of view, there's a balance between this entropy and the energy it takes to actually do something with this. So it turns out the computing power, the coding time, the source code and the memory goes up as entropy goes up. So it turns out most applications today are one-off affairs. We custom code them. We have a huge amount of surprisal in every message, so we have to write a lot of code. And that means if we just change the message a little bit, we have to write more code. And we create versions and re-releases and all those other things that we saw earlier. So this is high-energy computing when I have to do everything as a custom-built app. Now, the protocol of HTTP was designed to be low-energy computing. I can write an application in HTTP, and I don't have to change HTTP in order to get that new app running. HTTP operates on a low-energy model. Very predictable, very simple. But most things today still assume that HTTP would be the only protocol we would ever use. We've been at it for about 25 years. That's very nice, but do we think it's going to last 100 years? What happens when we're no longer using HTTP and get and post and put and delete? What happens if we're doing something else? What happens to all those machines? It turns out when you're using HTML and HTTP, like Abraham Maslow, when all you have is a hammer, everything looks like a nail. I can make everything work in HTTP. Well, of course you can. But you need to be prepared for the idea that HTTP might not be there. And then what do we do? Have you thought about it? Have you thought about how long this will last before it'll be gone? 25 years is a long time in internet time, by the way. So I talk about this idea of Kelvinism. Lord Kelvin was this geologist, and he was quite sure that the world would only be somewhere between 20 and 40 billion years old, but that's it, because he had measured the heat dissipation. And he had forgotten about radiation and lots of other things. And to his dying day, he could never accept the notion that he would be wrong. We need to be careful that we don't become Kelvinistic about what we think is going to happen on the web. So we need more designs, more message models that experiment with this entropy pattern. We need lots of low entropy, high information. We need to design for machines and not humans. And usually that means creating these structures that change the actual format from the information we want to give and from the actual protocol that we want to use. We won't talk a lot about this. You can look at the slides later. But we have laid out before us already enough technology to solve this problem. The higher the surprise in the message, the higher the dependence on code. We need to change that. There are all sorts of ways that we can start to refactor the code that we have to lower that surprisal value while still increasing the information value. There's a system called ALPS, which I and a few people are working on, which helps you sort of create a different kind of contract. So the contract has focused more on the domain surprise rather than on the structure or the protocol, and you can do the rest of that independently. Eventually, we need to start writing messages that only machines understand. There have been a few stories recently about how Google and Facebook have been experimenting with getting machines to talk, and they invent their own language that humans don't speak. So we'll see more and more of that in the future. So we need to stop thinking about protocols. We start to think about the fact that other protocols may exist someday. We need to focus on the network itself, not any individual thing as a protocol. It turns out the web is one application. It is this one place where we can begin to work things. And the web works on this very strange rule. It doesn't actually work in a random way. It works in this way where it actually favors connections. Google was founded on the notion of that the links favor connections. There's this thing called this scale-free networking. So we need to lower entropy, reduce dependence, and treat the network as the application we're working on, the machines we're adding to the application. Of course, there's some hard things too. We have to get past the point of central control. This is a thing called Conway's life. It's a simple mathematical equation, very small, but it generates an infinite number of art pieces that actually, some die, some live, some grow. We need to start thinking about the way that they will program things in the future when there's no central control. Stephen Wolfram has talked a lot about this. This is some of Wolfram's automata, cellular automata. The way von Neumann created computing CPUs and all that, he had a choice between that and cellular systems. He picked the CPUs because they were easier to do. But we've got a whole future in this version of automata, of treating every application as its own cell in a vast array of things. And this gets much closer to the way we start to see birds and ants and other things behave, when we start to treat the network as the application space. So machines have to learn to adapt. This is an example of a program called Robbie, which actually learns to find little objects. In this case, it was soda cans in a screen. And actually, you start with a random act, and then you do that 1,000 times. You find two that had the best score. You splice them together, and that becomes the start of the next 1,000 runs. And you splice the best two, and you splice the best two, and eventually it learns. What is that? Thousands die, a few live. This is exactly how evolution works today. So we already have people modeling this kind of activity. Modeling adaptation is another thing that we have to do. We have to figure out how people are going to favor one adaptation over another. There are a few bits and pieces that we'll talk briefly about. Random Boolean networks give us this idea of actually scoring things without any central hierarchy. It's just this sort of neurons that kind of get refreshed. And the biggest challenge is competition. In real life, the best learning instrument is death. You die if you don't learn. Now, we can model a lot of this in computing, but we haven't figured out how to do this well yet. And that's going to be a challenge for us. Okay, a quick summary. I know we've been through a lot, but we'll get a chance to talk about this a little bit. So we've talked about information theory and biological systems. It turns out that the web itself follows a lot of these rules. The problem is most of us, we ignore the features that we have available to us, this adaptation, this ability to get autonomy, because we have lots of tight coupling and we interdependence. We change one thing and the whole set of applications break. We have to start creating these low entropy systems that let us decouple things by treating machines as these little cells, and eventually we have to give up the notion that we control the machines. That's going to be very difficult, but that's what we have to do. We don't control most of the world around us, and the machines are going to be just part of that at the same time. So how long? I love this, Hofstadter's law. Things will take longer than you think, even after you take Hofstadter's law into account. So we don't know how long this will take, but we know that we can make a step every day. We know we can get a little bit better every day. Because if we ignore the mistakes of the future, we're going to make them. We need to get proactive today and think about how we can build safe, cheap, and effective automata. Because the rule of the robots is already here, and we might as well start to join and enjoin those robots into the things we want. So we must be willing to lose sight of the shore in order to go ahead. And I want to thank you very much. Hopefully this has given you some ideas, some things that we can talk about here in the break. And I just want to say thank you very, very much. Thanks. Thanks.